You know, all that metal in your phone, your car, even your jewelry? Ever stop and wonder how it goes from just a chunk of rock into something so pure and finished? Well, today, we're pulling back the curtain on the secret science that makes it all possible. It's called hydrometallurgy.
Okay, let's just jump right in. How do you take this, a piece of raw, totally unassuming ore, and somehow, transform it into this? Pure, gleaming gold. It seems like some kind of modern-day alchemy, doesn't it? Well, spoiler alert, it's not magic, but it is some seriously clever chemistry. And that science is called hydrometallurgy. It's all about using water-based, that's the hydro part, chemical solutions to literally pull metals right out of their ores. And you know what? That alchemy analogy is pretty spot on. It really is like alchemy, just powered by chemistry. Instead of a magic wand, metallurgists are using water and some very carefully chosen chemicals.
This entire process really just boils down to a three-stage journey. First, you've got leaching, which is where you dissolve the metal from the rock. Second is purification, where you clean up that messy chemical soup. And finally, recovery, where you get your pure metal back into a solid form. So leaching, purification, recovery. We're going to walk through each one.
So here's our game plan. We'll cover the basics, then we're going to break down each of those three key stages: leaching, purification, and recovery. And to really bring it all together, we'll finish up with a real-world case study on how gold is actually made. Let's get into it. All right, on to our first big step, leaching, or as I like to think of it, freeing the metal. The challenge here is simple, but, well, it's huge. Your valuable metal is completely locked up inside solid rock. How on earth do you get it out? This right here is the perfect analogy. Just think of it like you're brewing coffee. The hot water is your solvent, and it selectively dissolves all the good stuff. The caffeine, the flavor, while leaving the useless coffee grounds behind. Leaching works on the exact same principle.
Now that hot water in our coffee analogy, it has a technical name, a lixiviant. This is the active chemical solution that does all the dissolving. And, well, these are a little more powerful than just hot water. We're talking about things like sulfuric acid for copper and zinc, or even sodium cyanide for precious metals like gold.
But you can't just throw any old chemical at any rock. For a leaching process to actually work, it has to be viable. That means it needs high dissolution. You want to get as much of that metal as you possibly can. It needs high selectivity, so you're only dissolving the valuable stuff, not the junk rock around it. And this one's absolutely crucial. It has to have a low cost. I mean, if your chemical costs more than the metal you're getting back, the whole operation is a bust.
Okay, on to our second stage, purification, aka the great cleanup. So, you've done it. You've successfully dissolved your metal. That's awesome. But now, you have a new challenge. Your metal is floating in what's called a pregnant solution, which is basically just a messy soup full of other impurities that came along for the ride.
So how do you clean that mess up? I suppose you could try to just boil off all the water and see what solids are left behind, but that's incredibly inefficient and super expensive. The much smarter way is to use a kind of metal magnet to just pluck only your target metal right out of the solution. And this metal magnet is called a carrier phase. It could be a solid, like little granules of activated carbon, or even a special liquid solvent. The key is, it's designed at a molecular level to have this high, super selective affinity for just the metal you want. It attracts and grabs onto those metal ions, and it pretty much ignores everything else in the soup. Okay, let's see how this whole metal magnet thing works in the real world. We'll look at one of the most common methods for gold processing, a process called carbon in pulp. Okay, I know this diagram looks a little complicated, but the idea behind it is actually brilliant. So you've got your slurry, that's the mix of dissolved gold and rock particles, and it's flowing through a series of tanks in one direction. At the same time, you have these small granules of activated carbon moving in the opposite direction. As the carbon tumbles through the slurry, it just acts like a sponge, absorbing the gold ions right onto its surface. It's so clever. And this graph shows you exactly what happens. As the process moves from one tank to the next, check out the gold concentration in the solution, that's the dashed line. It just plummets. Meanwhile, look at the concentration of gold on the carbon granules, the solid line. It climbs up and up. It's just an incredibly efficient way to transfer the gold from the liquid onto a solid carrier. And that brings us to our final stage, recovery, or getting the metal. We're at the last challenge. Our metal is purified, it's concentrated, but it's still chemically attached to our carrier phase. So how do we get it back into a solid, pure form we can actually hold in our hands? The secret to this whole final step lies in creating a very specific chemical state called supersaturation.
Supersaturation is really simple. It's just when you force a solution to hold more of a dissolved thing than it naturally wants to. Imagine you're making iced tea. You can add a little sugar, stir it in, but eventually you hit a point where it just won't dissolve anymore, right? It just starts piling up at the bottom as a solid. That's it. You've supersaturated the tea with sugar. We do the exact same thing to force metals out of a solution.
And this diagram shows us how metallurgists control this with incredible precision. They don't just dump everything in at once. No, they operate in this very specific metastable zone. See, if you have too much supersaturation, that liable zone up top, you just get a flash of tiny, often impure crystals. But if you can stay in that metastable zone, you can encourage the metal to precipitate slowly, which favors the growth of large, pure, high-quality crystals. That's the good stuff.
And there are a few key ways to make this happen. You can use precipitation, which is basically changing the solution's chemistry to make the metal suddenly insoluble. There's electrowinning, which uses an electric current to plate the pure metal onto a surface, kind of like chrome plating a bumper. Or you can use this fascinating process called cementation, where you add a more reactive metal to basically kick your valuable metal out of the solution and take its place.
All right, let's look at our case study, gold. Let's put all three of these stages, leaching, purification, and recovery, together and see how they actually work in a real-world processing plant.
So, first up, the leaching circuit. The raw ore is crushed into a superfine powder and mixed with water to create a slurry. Then, the key ingredients go in: lime to control the pH, and our lixiviant, sodium cyanide. Air is then pumped into these huge churning tanks to provide the oxygen needed for the chemical reaction that dissolves the gold into the solution. Next up, in what's called the cementation circuit, we see our purification and recovery steps happening all at once. The gold-bearing solution is first clarified to get any solid junk out, then zinc powder gets added. Remember cementation? The zinc is more reactive, so it jumps into the solution and literally forces the pure gold to precipitate out as a solid sludge. This is the moment the gold becomes solid again.
But the journey's not quite over. That gold sludge is then filtered. It's treated with acid to get rid of any leftover zinc, and finally, it's smelted in a furnace at incredibly high temperatures. And the result of all that chemistry? Pure molten gold, which is then casted into those iconic bullion bars we all recognize.
So there you have it. From rock to riches, hydrometallurgy isn't magic, but it is some really elegant and absolutely essential chemistry that unlocks the materials that build our entire modern world. It really makes you think, doesn't it? What other hidden industrial processes are out there, shaping our lives every single day?